Good evening, everybody. Welcome once again to the Food for Thought public lecture series from the Macdonald campus of McGill University. The theme for this year's series is Celebrating McGill's Bicentennial and the Promise of a Better Tomorrow. I'm Grant Clark. I'm an associate professor in bioresource engineering and one of the organizers of the series, together with Anna Duff and Ingrid Shiraz, who are both here with us tonight to help things along. I'm also a descendant of Northern European settlers, and I work and live on unceded Indigenous territory. The Kanien'kehá:ka Nation are the custodians of Tiohtià:ke, the territory on which McGill University stands, and of the surrounding lakes and rivers. To the south of Montreal is the community of Kahnawake, and to the west is the community of Kanesatake. And I thank these people for having watched over these lands and waters for so long and for continuing to look after them today. I'd like to remind you that this lecture is being recorded this evening. Please keep your audio muted during the lecture. We will monitor the chat window and relay any questions to the speaker if you wish to ask questions in that way. There will be a question and answer period after the presentation, and you're welcome then to ask your questions verbally if you choose to, or again, you can leave a note in the chat. I'm very pleased this evening to introduce our speaker, Professor Chandra Madramootoo, familiar to many of you. He is a James McGill Professor in the Department of Bioresource Engineering and a former Dean and Associate Vice Principal of Macdonald campus. He's the Director of the McGill Water Innovation Lab, a member of the UN Food and Agriculture Organization Steering Committee on the Global Framework on Water Scarcity and Agriculture, Vice Chair of the International Development Research Center's Board of Governors, Founding Director of the Brace Center for Water Resource Management, President of the International Commission on Irrigation and Drainage, inductee to the International Drainage Hall of Fame, and winner of the World Irrigation and Drainage Prize, to name a few of his illustrious accomplishments. So he's going to speak to us today on the topic of how water use in agriculture has changed over the decades. And Chandra, I turn the floor over to you.
Thank you very much, Grant, for your introduction. And I hope everybody can see the screen. Perfect. Okay, well, good afternoon, everybody. And it's a real pleasure for me to say a few words today, and literally a few words about how water use in agriculture has changed over the decades. This is the entire subject is something of the order of about 30 or 40 individual lectures that I have given or I give in my courses in irrigation, drainage, and water management. So it's a tough job to try and condense so many lectures and lecture material into something that's only going to be about 30 or so minutes long. So I'm going to give a very high level overview and try to skip a lot of the details, but I'm more than happy to answer any questions that you might have at the end. So as Grant mentioned, the title of my talk is How Water Use in Agriculture Has Changed Over the Decades. And I hope that by the end of the talk, I'll give you a little bit of a glimpse as to what I see in terms of the future of the continuing changes that we will see in water use in agriculture. Well, before I get into the topic specifically, I want to take this opportunity to dedicate this talk to a few people who have made a remarkable impact on my life as a student, primarily as a student, but also as colleagues here at Macdonald College. I want to, first of all, pay tribute to Emeritus Professor Mark Waldron, who graduated from Macdonald in agriculture, late Professor John Ogilvie, who was the chair of the engineering department when I entered as a student in engineering. And John is a graduate of the class of 54 and was very instrumental in introducing me to a lot of topics in the profession. John was an exceptional engineer and instilled in us as students engineering principles and design theory and computers. At that time, in the mid-70s, computer usage had just begun to take off, and John actually was very instrumental in helping to get me started as an undergraduate in computer engineering. I also want to pay tribute to Cameron Mirza, who is here with us today, and Cameron is from the class of 6-1, and welcome, Cameron. Unfortunately, both Emeritus Professor Mark Waldron and John Ogilvie have since passed away. But I also want to say a very special dedication and tribute to somebody who has been a major professor to me, served as my advisor in my graduate program and thesis supervisor, a colleague in irrigation and drainage engineering, and the person who helped to establish my career in irrigation and drainage engineering here at McGill, and none other than Emeritus Professor Robert Broughton, PhD 1972. And I owe much to Bob for what he has done to my career. And I also want to pay a special tribute to a late Emeritus Professor, Professor Angus Mackenzie, Professor of Soil Science, who was so instrumental in doing so many things for me and also launching my career at Macdonald, for mentoring me and shepherding me through my academic career. And it was a pleasure to be associated with Gus for many, many decades. And I'm pleased to see that his wife, Joan, and daughter, Sue, is here with us. And I extend a special welcome to them as well, and for all that Gus has done for me. As you can see there, Gus is in his much younger years. I think Sue was trying to tell me the age of that picture at one time. And with a much younger principal of McGill at that time, David Johnston, who was also a tremendous leader of McGill and principal of McGill. So I dedicate this talk to all of them. Now, to put this into perspective, and as I said, I can't cover every single aspect of water, irrigation, and so on in this talk, but just to put it into a slight perspective here, you'll see that the total water withdrawals, freshwater withdrawals in the world approaches something in the order of 5,000 cubic kilometers per year globally. And you'll see that irrigation is actually quite high. You'll notice that with irrigation, we're consuming just about 3,500 cubic kilometers of water per year in the irrigated agriculture sector. And agriculture via irrigation uses somewhere between 70 to 95% of the fresh water consumed in various countries. For example, in the Aral Sea Basin of Central Asia, which we'll refer to later on, about 95% of the water that's withdrawn from the Amu Darya River and the Sir Darya River ends up in irrigation. And the same thing happens in Egypt. About 85% of the water that's withdrawn from the Aswan Dam is the High Aswan Dam, goes into irrigation primarily in the Nile Delta, but in other parts of Upper Egypt. And you'll see the consumption with livestock and domestic use remain fairly constant, but irrigation is quite high. And the challenge that we have in irrigated agriculture is how much longer are we going to have the luxury of being able to withdraw that much amount of water towards irrigated agriculture, given the competition from other sectors, given the concern about conservation of water in agriculture, because being able to conserve water in agriculture also means that we'll be able to better protect water quality from agricultural lands. And so that's really the background to what I want to talk about today in how irrigation is evolving, recognizing that it is the highest consumer of global fresh water, and we need to do much more and focus much more of our efforts on reducing water consumption in irrigated agriculture. So if we think about water scarcity, and you're all quite familiar with the global debates about scarcity of water, fresh water, people not being able to get adequate amounts of water as we can in, at least in Canada and in parts of Europe. And also the situation with respect to food security, that we need to be able to meet the food demands of the future. And it's estimated that we would probably have to double food production to be able to meet the growing demands of food in the future. So what is the role of agriculture, irrigated agriculture? Well, irrigation, as you can see here, the irrigated lands of the world cover about 300 million hectares of land worldwide. That's about a fifth of the whole cropland in the world, about 1,500 million hectares. But importantly enough, or significantly enough, it produces 40% of the world's food. So quite a large amount of water goes into producing 40% of the world's food, and we can't ignore that. We have to continue to improve the performance of irrigation systems with the constraints of land and water availability, but the demand for food. And we also can't ignore the rain-fed areas in the world. So as you can see here, there are roughly about 1,200 million hectares of rain-fed land, varying amounts of rain-fed agriculture from sub-Saharan Africa with minimal rainfall to much larger areas. For example, Canada, that's where there's much more rain-fed agriculture. So we can't ignore that either, but the focus today will be really on the irrigated areas. Well, to be able to put this also into some perspective of how we think about working on this problem, we look at the hydrologic flows in irrigated agriculture. And so as we withdraw water from lakes and rivers, reservoirs, some of that water is lost at the source in terms of leakage, evaporation over reservoirs, and also in terms of seepage. And this was one of the big problems of irrigated agriculture in southern Alberta up until about the 1990s, that there was quite a bit of water going from canals, leaky canals, unlined canals to into seepage, and that would create salinization and waterlogging. And all of those are non-beneficial uses of water in irrigated agriculture. And then when we get to the field application, where we transfer that water from aqueducts, pipelines, canals, smaller on-stream reservoirs onto the field, and we have siphons and radial turnouts onto the field, we have two forms of water uptake, as you can see here. We have the beneficial consumption by the crops. So that is the water that's delivered to the field that goes into the crop through photosynthesis to be able to produce biomass. But we also have water that goes into on the top of the soil and also to the crop that doesn't get used for the beneficial production of biomass. And so we get soil evaporation, we get wind evaporation, and that's non-beneficial consumption. And also on the field, we have non-recoverable seepage. So we put on a lot of irrigation water. Some of it gets used beneficially, and some of it goes down below the root zone and leads to accretion of the water table. And some of it goes as return flow back into rivers and reservoirs. Well, that is not of use to the crop either. So a lot of our focus today is on trying to reduce these aspects or components of non-beneficial consumption. Reducing return flow, reducing the non-recoverable seepage. And the point of doing this is not only do we conserve water, but as I mentioned before, there's the water quality aspect. And so as water moves through the soil profile, it takes chemicals with it and takes salt with it in the arid and semi-arid areas. And therefore, we're returning water downstream of a much lower quality downstream into the canals and the rivers, which renders that water unusable for downstream communities. And that's the other driver and driving force as to why we want to focus on the beneficial consumption and reducing the non-beneficial consumption for those various water quality reasons. So to give you an example of this, one could not take a better example than the Indus Basin irrigation system. It's the largest contiguous irrigation system in the world. And it irrigates something close to 50 million acres of land between India and Pakistan. And it does this particularly since an agreement was signed at the time of partition between India and Pakistan and brokered by the World Bank through a series of dams of rivers of the branches of the Indus in India and Pakistan. Barrages, headworks were constructed, as you can see here from these dark black lines. And as water moves through those canals, it then goes into distributaries and irrigation ditches and miners and distributaries into the fields, and farmers then take water off from those distributaries at the tertiary or quaternary level scale. So just some statistics here. You'll see that there are three major reservoirs, about 18 barrages, 12 link canals, 45 canal systems, 107,000 kilometers of watercourse taking water into fields. And then you have the length of canals, the average water diversion, about 105 million acre feet, and groundwater abstractions are about 45 million acre feet. Interestingly enough, there are a large number of tube wells in the Indus Basin because of all of the problems of surface water distribution, inequality of surface water distribution, improper rotational supply of water. Farmers take the water management into their own hands by putting down their own private individual tube wells. And that is also a source of concern because we're pumping groundwater, abstracting groundwater at a very unsustainable rate, and also rather low quality groundwater. And that water, which at one time when they put down those tube wells were shallower, 20 meters or so from the ground surface, now that water table has dropped and it's even deeper. And you'll see here that there's a note that about 40 to 60% of water losses occur in that distribution system. And that has been the focus of trying to put in lined canals, trying to reduce evaporation from some of the reservoirs. But because the system is so large, it's very difficult to try to manage it on such a large scale as we can do on smaller irrigation schemes. So these are some of the examples of where water is being lost in conveyance, even before it gets onto the field. You'll see here at the top left-hand corner, the dam in China, the Three Gorges Dam at the time of construction. On the top right-hand side, the El Salam Canal in Egypt that was built to take irrigation water into the Sinai, and also conveyance through pipes and different diversion weirs and bifurcation systems with gates that are not accurately controlled or fitted, and so losses occur along all of these points. And then you have field application losses. As we put water on the field, as I mentioned to you, what's really beneficial is knowing what the evapotranspiration is, because that gives us the crop consumptive use of water for that particular crop. And so each crop having its own consumptive use. And that's where we also get, as from these pictures show, a fair amount of losses at the field scale as well. So this, I'm not going to go through this in much detail, but it gives you an idea of, along the Indus Basin, the amount of water that is being lost along the system. And you'll see where we have a large amount of water that's returned to the Arabian Sea from the Indus Basin. So the water starts being collected in the Mangala Dam, Tarbela Dam, and it goes down to the Arabian Sea through the provinces of Baluchistan, all the way down to Sindh at the border with the Arabian Sea. And there we have something like about 33 billion cubic meters of water that ends back up into the Arabian Sea. That is primarily return flows and seepage and leakage losses and so on. But the difficult part of this is that much of the water that goes back into the system along the length of the Indus Basin is the level of pollution and the amount of salt that ends up in the Indus Basin going out into the Arabian Sea. And it's not uncommon to hear the people of Sindh, Karachi in particular, where that outfall occurs, complain about the amount of salinity in the water that's coming from the upstream provinces with poor irrigation management. So if we put all of this together and we look at the efficiencies at every single point along the system, you'll see there that the overall irrigation efficiency is only around 36%. In other words, only about 36% of the water that's diverted is beneficially being used on cropland, which means that there's about 64% of the water that is lost even before it's consumptively used by the crops, which is significant when we think about the losses. But when you look at the scheme, you look at the jurisdiction between the provinces and two countries, and the amount of water users associations and water districts, it becomes very difficult to see how, with that complex system of management and governance, one is able to successfully reduce such losses. And this remains a challenge, a huge challenge for the Indus scheme as a whole in trying to improve water use and the quality of the water. And Canada has played a role. I'm not sure if Professor Broughton is on, but he did a lot of work in the Scarp Mardan area with Ali Shadi from CEDA and others, and on the left bank outfall drain, trying to improve the drainage and the water quality from these high water tables. And one of the impacts of this has been the twin menace of salinity and waterlogging as a result of such inefficiencies. And this now restricts the ability of the use of that land for productive crops, because once you start to get over 4, 6, 8 decisiemens per meter in the soil, there are very few crops, large commercial crops, that can withstand that kind of electrical conductivity in the soil. So we have arisen the water table from the over-irrigation, and we also have salt being built up in the root zone, and the pure water evaporates. The crop is left to take up saline water in the root zone, which, as I said, is injurious to crop growth. It's estimated that we have roughly about 30 million hectares of cropland globally around the world that's affected by salinity and waterlogging. So about a fifth of our irrigated area is affected by salinity and waterlogging. This is also seen in Uzbekistan, where we had a chance to do about 12, 15 years of work in Central Asia. And you'll see here the two main rivers that drain into the Aral Sea. At the top here, you have the Sir Daria River, and at the bottom here, you have the Amu Darya River, all draining into the Aral Sea. Well, the Aral Sea was one of the richest freshwater lakes in the world, and supported a variety of fisheries, habitats, aquatic habitats, wildlife, and various aquatic species. Unfortunately, during the time of the Soviet Union, when this was all part of the USSR, this was the large cotton growing area of the Soviet Union. And the countries, as you can see here, Uzbekistan and Turkmenistan, Tajikistan, they were the large cotton growing areas. So a lot of this area got converted into irrigated land, not necessarily for food production, yes, for some food production, but mainly for cotton production, because it brought in foreign currency into the USSR. But it was all done at the expense of environmental degradation. And so you can see the green, you can see the green areas of cropland around here into the Fergana Valley in here, which is quite a fertile area where we've done some work that I'll talk about in a minute. But that water that got diverted into agriculture meant that there was less fresh water going in to the Aral Sea on both the Sir Daria and the Amu Darya rivers. And the quality of the water that went in was also quite poor because of all the return flows that I mentioned before, taking salt and chemicals with it into the Aral Sea. We saw quite a large-scale destruction of the Aral Sea ecosystem. And unfortunately, none of this was really known until the collapse of the Soviet. The full extent of it wasn't really known to the Western world until the collapse of the Soviet Union in 1992. And also, I should mention that a special colleague of mine with whom I worked in the Aral Sea, unfortunately just passed away, Dr. Victor Duchovny, was the first person who brought this to the attention of the world. At the International Commission of Irrigation and Drainage, World Water Council, he brought to the international world the fact of this massive degradation with the water quality in the 5 republics, the destruction of the Aral Sea. And as a result of that, he single-handedly was able to motivate a lot of the donors, the World Bank, the former Canadian International Development Agency, to put funding in the European Union, to put funding into the restoration of the Aral Sea. So I wouldn't go through all the statistics here with you, but just to point out that, roughly 5 million hectares of cropland were affected by salinity and waterlogging in the RLC basin. Poor irrigation practices, dilapidated irrigation canals that were not properly maintained, high losses due to poor field application methods, primarily surface irrigation methods. And you can see here parts of the RLC where once a thriving fishing industry, we have rusted out fishing boats and so on at the bottom of the RLC. So, you know, the point is that irrigation, while playing a major role in feeding the world, has also led to some major environmental disasters and water quality disasters. And so there's that added pressure to try to improve the performance of irrigation systems from the environmental standpoint as well. So we have a limited amount of land area available for crop expansion. And that's why we just can't expand our irrigation as well. We have problems of trying to supply water in many of these areas that are shown in red: Middle East, North Africa, the MENA region. And we also see this in India, in China. And one of the problems is that some of these large green areas in South America, for example, there are parts of very fertile ecosystems, rich ecosystems that need to be protected from an environmental standpoint because they support a lot of different species. So we really can't say ignore all the lands that we've degraded. We'll just continue to degrade and we'll move into other areas because that would spell a much graver disaster for us in the world. So where have we been focused at this point in time? This is just a similar type of diagram that I showed you before with the hydrologic flows. And here's where we have put a lot of our effort into trying to improve this beneficial water consumption. And we have been able to do it with some success. There's still many unanswered questions and much more work remains to be done, but that's where a lot of the effort is being placed at the moment. So some of the first things that we saw in trying to improve that beneficial use of water, we saw in the mid-1980s, the introduction of drip irrigation. And you'll see here, you have the drip irrigation lines along some onions. The water goes directly from that drip pipe into the soil. We cut down the evaporation. We cut down the seepage and the percolation losses. We used buried main lines to supply that water to the lateral pipes. And so we reduced the leakage from canals and ditches as well. And so about over 90%, 90 to 95% of the water that is being delivered is being taken up by the crop for beneficial production of biomass. So that's was really the first start to this. And then we saw much later on, probably within the last 15 to 20 years, the introduction of these LIPA systems in the more advanced developed countries of Europe and North America, parts of South America as well. These LIPA systems, low energy, low pressure systems that bring water directly to below the crop canopy, directly to the root zone of the crop. So we cut a lot of the drift and the spray of water by wind, and we try to use these low pressure systems with low energy to get the water directly into the cropping system. So, you know, that's been sort of the trajectory that we have taken over the past few years to try to help and improve that beneficial water use. This is some of the work that we did in the Fergana Valley with Victor Duchovny and his colleagues with the Irrigation Center of Central Asia, and working with a couple of my graduate students, we started to look at better furrow irrigation, because in these parts, as in many parts of the developing world, you can't do drip irrigation that easily because of the type of crop. Drip irrigation works best with orchard crops, row crops, and they don't have the financial capacity to implement some of these LIPA systems. So what we've done here is to work on land leveling, furrow irrigation, straighter furrows, and also shorter furrows to get better distribution of water from the main ditches. We put in here triangular flumes to regulate the amount of water going from the ditches into the furrows to get better water distribution and better metering of the water based on the crop demands. And so, as I said, we've had some good success with this, and some work that has been published by my graduate students on alternate furrow irrigation. And so here's a crop of soybeans, and instead of, in the Fergana Valley, having water run down each furrow, as I said, we shortened the furrows to get better distribution. On certain days, we would have water go down certain furrows rather than every furrow. And we were able to increase the water use efficiency with bean crops and looking at alternate irrigation, furrow irrigation, and also at deficit irrigation as well. And this has been an area in which we think there's a lot more potential in some of the developing world to help to improve water use efficiency. Now, here's a success story to some extent, depending on who you talk to, but it took a 10-year drought in Southern Australia to be able to bring these innovations. And this is the millennium drought that occurred in Southern Australia, 4 of the states, from Victoria going all the way down to South Australia, passing through the ACT, the Australian Capital Territories, and also through some of the parts there of Queensland. And this is actually a very fertile area. It produces most of Australia's food. It's a $40 billion Australian dollar industry, but that millennium drought created quite a bit of water scarcity and water shortages in the southern part of Australia. And as a result of that, the 4 provincial states, together with the federal government of Australia, they have a very similar governance structure as we do in Canada between the provinces and the federal government. They all got together and came up with a plan because there are 2 major rivers that go through here, the Murray River and the Darling River, and they came up with a management plan to help to keep that $40 billion agricultural industry going, sustainable, to keep farmers and irrigators in production. And so there's roughly about 800 million hectares of, 800,000 hectares of irrigated land between the Murray Basin and the Darling Basin that had to be protected from drought by improvements to the irrigation system. And one of the things that happened during that millennium drought period is that they had a tremendous salinity problem because it is a semi-arid area and they just don't have enough precipitation to keep the salt out of the irrigation system. So they came up with actually both an irrigation management and a combined salt management program that I think has been one of the biggest success stories we've seen in the industry. Several people are trying to learn from it and to use it, but it's not easy. And depending on who you talk to, while the environmentalists feel strongly that it has been a good plan, it has helped from an environmental standpoint, a water quality standpoint. Some of the irrigators, smaller irrigators, will tell you that they have had to come out of the irrigation industry, and they were bought out by bigger irrigators. So there has been some fallout from it, but the key elements of that salinity management program was to improve irrigation efficiencies, application efficiency, both at the canal level, the distribution level, and at the field level. They developed salt interception schemes to divert about 400,000 tons of salt per year away from the two rivers. And there were state policies and programs that they put in effect by creating salinity zones, and they were able to reduce the salinity spread overall in the Murray-Darling Basin. And so as a result of this, they were able to return much more water to the environment, into the two rivers for environmental flows and for wetland restoration in southern Australia, from Adelaide out to the mouth of the Murray-Darling Basin, but also wetlands further upstream. But there were other elements of the Murray-Darling Basin Management Plan that I think are quite significant. And some people have looked at this, and it has been very difficult to implement in other countries for political reasons, social reasons, but they moved to water pricing and water markets. You were able to buy water from Australia on the Chicago Stock Exchange. They put in place a very strong monitoring and compliance program with respect to irrigation water uptake and distribution, environmental flows, and you were fined if you didn't comply with that monitoring program. There was a big community engagement and communication plan, transparency and accountability, and there was a shared responsibility between all the stakeholders of the basin, not just the irrigators, but also the forestry, the fisheries, and the indigenous people. As you know, Australia has a very large indigenous community, and they have had to incorporate the views of the indigenous people into their water allocation program. And to their credit, they brought the best science to bear on the topic, and they were able to bring key advisors in to help them with an adaptive management program using science and making that transparent. And as a result of that, it was very difficult to dispute it because the facts were there on the table for all to see. So here's been some of the effect of what they have done. You'll see at the bottom here, these are salinity levels that were measured at a point called Morgan, at the downstream end of the basin. And you'll notice when they had the millennium drought, they had these low flows, and therefore, they had done some work to start to put their management programs into place. And up here, you'll see what they have used in past data. They have been able to predict what would happen in the future. And you'll see how if they took no management practices into consideration, how high the salinity would have been compared to what they have done with their basin management plan. So they've been able to drop the salinity quite low, and they've been able to manage to keep that salinity quite low as well, as a result of all of these efficiencies that they have put in place with their irrigation system. So a major success story in my point of view, but as I said, very difficult to replicate it in many other places, including in California, that have looked at it, but have found it very difficult to implement for a variety of reasons, which we wouldn't touch on here. But one of the big things that they did, which I think has been a breakthrough in irrigation, and this was an innovation by an Australian irrigation company called Rubicon, is that they were able to develop these gates that are computer controlled, and these gates they're able to sense where the water level is, both on the upstream and on the downstream, and they moved away from a supply driven irrigation system where you had water constantly flowing through the gates to a demand driven irrigation system. And it's probably the only place in the world where we see this. And so at the start of the cropping season, you as an irrigator would tell the Water Use Association or the irrigation district what crops you're growing, how much water you need. They would then allocate that along the canals and the ditches, and you could not exceed your water allocation. But what they did is, instead of allowing the water to be continuously flowing, they were actually able to hold water back upstream in storage, and then they could release it outside of the cropping season for environmental flows and return flows. And they also monitor the salinity level as well. So they were able to determine, based on that, how much water they could safely release back to the environment. So very successful innovation that took place there, with these gates and the data being sent back remotely by telemetry to a control system at the offices of the irrigation districts. Now, I want to sort of close by touching on Canada. And I want to say that there has been a lot of work that has been done in Canada. As a matter of fact, Canada is an unwritten success story. And there's a lot to be, Canada has a lot to be praised for on what it has done in the irrigation industry, particularly in our two large irrigated provinces, Alberta and Saskatchewan to a lesser extent, and with BC and the other provinces. There's about 1 million hectares of irrigated land, but most of it here in southern Alberta and southern Saskatchewan around the Diefenbaker Dam. And some of the innovations that have taken place in Canada have been, there are about 11 irrigation districts in Alberta, and those irrigation districts have done an amazing job. The irrigators in those districts have done an amazing job in, first of all, trying to improve their irrigation at the field level. You can see here, back in the year 2002, just taking data from one irrigation district, Eastern Irrigation District, about 30% of their irrigated area was under low pressure pivots, LIPA systems. Today, close to 75% of their irrigated systems are now LIPA rather than the traditional overhead irrigation systems. They've cut down the amount of wheel move side roll irrigation systems tremendously. And importantly as well, they have cut down quite a bit of their flood irrigated land. Used to be, close to 30% of flood irrigation, down to about 10% of flood irrigation today. So irrigators, the irrigation districts have done an amazing job on their own, using their own money at the field level to be able to make these conversions. And then when we look upstream at what has gone on with the canals and the reservoirs, again, Alberta has used its heritage funds to do a lot of work on canal rehabilitation, canal lining, pumped pressurized pipelines rather than leaky canals to reduce salinity, canal seepage and so on, and waterlogging adjacent to the canals. So, that's an untold story that not too many people either in Canada or outside Canada are aware. And when we put all of these 11 irrigation districts together at the same kind of scale that they've done here, I think it's a remarkable story. You'll see here in southern Saskatchewan, potato production under LIPA systems as well. And certainly today, as some of you probably know, there's a push by the government of Saskatchewan together with the federal government to spend about $4 billion to do more in terms of irrigation, both in the Capel Valley and around Lake Diefenbaker and the west side. So taken up using all of this technology. There's the two governments putting together with the growers about $4 billion into this kind of expansion program. I think is building on all of the successes that have taken place is truly amazing. And so if you look at some of the data, this is some data from Alberta for barley production. It's quite interesting when you look at some of the trajectories here. You can see that back in the 1960s, they used about 900 millimeters of water for barley production. It's down to about today to about 380 millimeters of water, and projected to go even further down into the future as they continue to improve irrigation efficiencies. And when you look at their yields, taking barley again, 900 millimeters of water, 2.5 tons per hectare today, using about 380 millimeters, getting 6.5 tons per hectare, and with the genetics and proper field management, precision agriculture, for example, getting up to about 11 tons per hectare being forecasted. I think this aspect of water productivity, water use efficiency in Canada, and particularly in Western Canada, is a completely amazing story that can serve as a lesson for many parts of the world. So they've not finished some work that we have done with the government of Alberta, working on precision irrigation, variable rate irrigation. My graduate student, Dr. Aguiliari, who's online with us today, is the main driver of this work, where we have created management zones and fields that are affected by salinity, waterlogging, high electrical conductivity, depressional lands, and we've been able to regulate the water that goes over those irrigation zones. So collecting the EC data from one of the pivot circles, the elevation data with the digital elevation model, and trying to break this up into management zones in which we can apply water in each of these management zones as the pivot rotates around the field. And you'll see here, we've been able to get wheat yields as high as 4.8 tons per hectare in the highly optimized management zones, and in the controls yields about 2.2 tons per hectare with just regular management. And we've published this in the Journal of Irrigation and Drainage Engineering in the American Society of Civil Engineers. So, and just one of the many publications that has come out from that work. But we think that there's a lot more potential to do when you couple what has happened in Alberta so far with these kinds of technologies like precision irrigation and variable rate irrigation. Much more efficiencies could occur. Coming closer to home, some of the work that we did in Southern Ontario, in Leamington, with the large tomato growers who at that time were producing tomatoes for the Heinz plant in Southern Ontario. Myself and graduate student Dr. Samuel Homa did some work here looking at remote sensing to determine what was the evapotranspiration in fields. So we had a series of fields under tomato production, sandy loam, very sandy loam soil, and we looked at unmanned aerial vehicles with hyperspectral cameras and also satellite images, both Landsat and Sentinel from the European Space Agency. And we were able to generate these kinds of maps using the normalized vegetative index from those images that we took from the fields. And we were able to program an algorithm that would convert those NDVI images to the evapotranspiration. And because these satellite images can be obtained every 5 days or so as the satellites rotate the Earth, we can actually get a good real-time picture of what is happening in the field. And I think this is another advance that is going to be exploited a lot more in the future, of how we can make use of some of these remote sensing tools to give us real-time ways of determining water needs and requirements. And some of the results that we got there, if you notice with our algorithms and models from the remotely sensed images, we were able to calculate in 1 year over the whole growing season a need of about 165 millimeters of water, compared with what the irrigator was doing, where they put on in that year about 200 millimeters of water. And the same thing in 2018, about 190 millimeters of water that we programmed from our algorithms, compared to what the irrigator was doing with 247 millimeters of irrigation water. So under very constrained, water limited, irrigated conditions, there's a lot of room here, as you can see, about a 16 to 20% reduction of water that could be obtained with these kinds of technologies to try to improve water use efficiency. And I think the future is terrific when one looks at what's going on now in the world of big data and Internet of Things, where we could collect all kinds of environmental data and soil moisture, water data, electrical conductivity data in the field. We can send that data up into the cloud. We can process that data with some of these high-speed computers, but given the large volumes of data that one could collect, and working towards trying to make this applicable to the irrigator by putting it onto an app on an iPad or a phone. So the irrigator doesn't have to worry about all the processing. He or she doesn't have time to do all the processing, but if we could do all the processing from behind and present the data to the irrigator to be able to use on a real-time basis, I think would be a tremendous advantage. So I'll stop here. I think I've well past my time, and I'd like to thank all the graduate students who have been participating in these projects, all my research collaborators around the world, and to all our funders, NSERC, Ag Canada, CFI, FDRNT, the Max Bell Foundation, and of course, McGill. So Grant, I'm sorry I went over, but I'll be happy to answer any questions.
Thank you very much, Chandra. I really appreciate the time you took to give us this stimulating talk. Very informative. I will open the floor to questions, and I'll read the questions from the chat in just a moment. So, Dr. Madramootoo, we have a question from Peter Morrison, and he's asking, pardon me, what does the efficiency of water use depend on in respect to seasonal fluctuations in rainfall? Is water use efficiency likely to decline with an increase in climate change-driven extreme events?
No, and I think, Karen, you have something similar as well, a similar type of question about the impacts of climate change. Well, what we saw in the IPCC report that came out on August 9th is that we will see much more severe climatic events in the future as we try to keep within this 1.5 to 2 degree limit. The chances of us being able to do that are pretty slim, as that report shows. And as a result of that, we will see much drier periods. We'll see lower rainfalls during the dry periods. We'll see prolonged periods of drought as well. That is going to happen. We already see some of it. I mean, for some of my colleagues from Western Canada, we saw it this year in Saskatchewan and Alberta, of the effects of the drought leading to forest fires and so on, and agriculture being impacted, where farmers couldn't even get a crop off the ground this year. So that is a reality that we're faced with. And one of the things a few years ago, some of my colleagues in Agriculture Canada asked me to make a presentation to the deputy minister and assistant deputy ministers about the fact of how we could use irrigation for drought proofing. And I think that has been, it's taken quite a few years, but I think that has been one of the drivers that we see both the government of Alberta and the government of Saskatchewan now put in money in to these irrigation expansion projects, because that is the reality. And so the question that Agriculture Canada asks itself, the policymakers in Agriculture Canada, can we continue to keep paying out, making out drought payments, or is it not better to put that money together with other monies into a expansion or series of expansion projects that would ensure that the irrigators then have water to be able to have production? And the obvious answer is yes, we're much better off to do that, to support the irrigators. And I think that the question that sometimes get asked is, well, will there be enough water in a change in climate to support that irrigation expansion? And I think this is where these efficiencies come in. Yes, we can support that expansion, and we can enable the irrigators maybe not to have the full amount of water that they currently are accustomed to, but we would be able, with, if these efficiencies and new technologies are implemented, be able to sustain yields a little bit higher, or a lot higher, than having no yield at all. So it's a question of how we can do more drought proofing through improved irrigation efficiencies and water management.
Thank you very much, Chandra. I have another question here from Marilyn Scott. So you've done the easy questions. Here's one that's a little harder. She says, you've noted that part of the challenge of water losses due to irrigation is the projection that food demand will double over the next few decades. Can you comment on how much of the need for irrigation water could be reduced by increased focus on reducing food waste and a shift toward eating a diet that is more health promoting?
Well, Marilyn knows the answer to that question. I don't think she needs my response. Yeah, sure, Marilyn, obviously. If we were to, and by the way, this has been a major topic on recently in the United Nations Food Systems Summit, of which I've been a participant and a contributor. And that came up quite a lot by groups across the world, that if we were to move away from less animal agriculture, for not just in terms of water, being able to use less water, but reduce greenhouse gas emissions. This also would help to play a big role in terms of climate change and reducing our water and carbon footprint and putting more carbon into the soils. So yes, absolutely. Diet diversity, moving to a more plant-based system, plant-based diet, less meat in our diets, for sure would play a significant role. And that is something that I think we all need to pay attention to. There was a paper that was published in the summer of this year. I actually have it in my presentation. We didn't have time to look at it. There was a paper published in PNAS by a couple of people from Europe and one from the US on this whole aspect of sustainable intensification and irrigation being able to be used for within as part of that sustainable intensification. And I don't agree with some of the assumptions that they have used in that paper, but they have indicated that should we pay much more attention, should we differentiate storage systems between large storage, medium storage, and small storage systems, we might be able to intensify agriculture, particularly cropland, but taking into account what I've said with less use of crops for livestock feed, that we could meet the food demand for projected to occur. by the year 2050 and this doubling of food. But, you know, again, your point on food loss is well taken. That was a big topic in the United Nations Food System Summit. The whole question that we need to do a lot more than we're currently doing. We put a lot of water, a lot of carbon, nutrients into producing food, and then we don't consume it, we waste it. So yeah, for sure. But as I said, Marlon knows the answer to all of this. We cut food waste, we moved to more of a plant-based diet, less animal agriculture. Absolutely, we'll be able to meet the food demands. I have a positive view on this. I'm not a pessimist by nature. And so I think that if we were to pay heed to these things, we would be able to achieve the food self-sufficiency that we're trying to get to.
Thank you very much, Chandra. If you'll indulge me, I'll just open the floor to see if anyone has questions they would like to ask verbally. So feel free to turn on your audio. You can unmute yourself and ask a question if you like. Don't be shy. Yes, Fred, you have a question?
All I've got to do is figure out how to run this machine, first of all. Chandra, thank you very much. That was a lovely talk. One question I would have is concerning the Aral Sea. And, you know, we have spoken about this at different times in the past. Mm-hmm. And I was always of the impression that under the Soviet schemes, they just plain took more water than they were able to do that. Now, since the Soviets are gone, and they're back now to having perhaps a more logical application of this, has the hydrological cycle come back sufficiently to be able to build up more of a reserve in the sea?
Good question, Fred, and actually good to see you. And thanks for that. Yes, we have talked about this before, and so I'm glad to continue it with you. Fred, no. The fact of the matter is that the Aral Sea is nowhere near to coming back to its once pristine or natural state. Yes, your first point that the Russians were totally indiscriminate in their use of water. They paid no attention to the removal of how much water was being used in irrigation. It was a free-for-all, and they thought by putting more water on, you got higher yields and more cotton, and then you know, more foreign exchange coming into the system. Well, that didn't quite happen. No. They have implemented some conservation practices, yes, but on very small scale. I think the Fergana Valley, which is where most of the irrigation is in Uzbekistan, they have been able to implement some of the practices. But, you know, politics and governance is still playing a role in those countries from a variety of perspectives, in that the Uzbekistan government still has not taken up some of the things that the policymakers and the technocrats like Victor Duchovny worked long and hard for in terms of implementing reforms. You know, technology will take us that far, but as we see from the Australia case with MurrayDarling, in the MurrayDarling Basin, it wasn't just technology. You know, they put in place all the water pricing. They reformed their irrigation districts for more transparency and accountability. There was monitoring, there was compliance associated with it. And that's, you know, very foreign to the 5 Central Asian republics. So they haven't gone that full breadth to be able to achieve the kinds of things that you and I would like to see. But there's also one factor that's complicating all of this, which I think you know quite well, Fred, and that is that this hydropower development has taken place and is taking place much more, particularly in Turkmenistan, is a threat to coherence of that water governance system in Central Asia, because Turkmenistan has decided to go on its own. They're up at the upstream, the headwaters, and they have decided they are going to expand their hydroelectric production capabilities. And they have said to the other republics, well, we'll supply you with energy and you supply us with food. And, you know, that kind of barter arrangement doesn't work. So unfortunately, and I know you have spent a good part of your career working in hydropower, is I think that the hydropower situation there and trying to sell power to Afghanistan and to Pakistan as well, I think is really complicating that whole water management and water resources picture in the Aral Sea Basin. I hope I've answered.
Yes, thank you. Thank you, Fred, and thank you, Chandra, for your response. I see that Jane has managed to turn herself on. So Jane, if you have a question, I'll take this as the last question of the session this evening.
Okay, mine's from a completely different perspective. Mine's from being home alone for 2 years almost with COVID. Food supply becomes a tremendous issue. You can't go out. How are you going to get your food? And I've always been an advocate of a sort of do-it-yourself from way, way, way back when. But with these, and I have to say what you're doing is really fantastically interesting. It's on such a global scale, large scale, et cetera, et cetera. But I do believe that most of the food supply of the world comes from small farmers, et cetera, et cetera. I forget what the percentage is, but it's high. And I think that's a tremendous resource that is being maybe overlooked in the food supply. And you know, I guess, you know, where there's this large institutions, there's a certain amount of control, et cetera, et cetera. But, you know, there's a lot of destruction going on with the fertilizers and whatever, and whatever, and whatever. They're positive, negative, that's it. However, with the hydroponics that are going on a large commercial scale, I believe that you guys out at McGill should be pushing for small scale in your home, you know, peered, whatever, and develop a system which could be put into homes. And guess what? If you look around, almost every home has lots of water running off. They all have, you know, pipes running. That water's gone. You know, if you just put a barrel underneath those pipes, you could keep water going, not as runoff waste, but you could use it to keep your gardens going, outside maybe in the summer or inside in the winter. And that would be a tremendous saving, where water would be used to increase food supply. But I don't know what kind of organization there is going on to further that kind of research leading to something practical. I listened to your I love these lectures. I love them. And I could see that there was a hint of it a year or so ago that someone was doing something downtown, etc. But it was on an industrial basis. But I think that would be a great something for McGill to research and go out and let people pick it up, etc. But it provides the basis to save water and increase the food supply. So we don't have to truck, we don't have to, etc. It would be perfect. And you know, most of the people I speak to, you know, you can see my generation. And there is a link to what you said way, way, way back when. However, I think that is something that most people would be interested in, because most people now have their gardens. Most people have their gardens, but they need a little help because they're they're really, starting out from scratch, and you guys are the professionals. So I think that's a whole area that McGill could, or maybe you're already doing it. And so I'm interested in your input, but that's obviously it's from a different perspective than your talk. And I thank you for your talk. It was really, really interesting.
Well, Jane, thank you very, very much for your comments. And I'm sure Grant could add some more, but you would be surprised. So first of all, I should say that there's something called the McGill Sustainability Systems Sustainability Fund, the McGill Sustainability Fund, MSF. And there are a lot of students who apply to this fund quite successfully to do exactly the kinds of things that you are talking about. I'm supervising some of them, by the way, in some of our design projects. And these are students who are working on exactly what you're saying. They're building these systems, they're testing them in the lab, and they're taking them out into their own homes. And that's exactly what they're doing. They're calculating all of the amount from the rainfall, how much runoff they can get from the rooftops. They're doing designs on different shapes of rooftops, from flat rooftops to peaked rooftops at different angles. And they're designing systems to collect that water, to store that water, and to put it into garden production vegetables. So I can think right now there are about 3 or 4 projects that are going on right now on campus, and these are student-led projects that they're taking the initiative and they're doing it. And I think it's a tribute to our students who are applying to this McGill Sustainability Fund, very successful at it, and implementing exactly the kind of project that you're talking about. So Grant, I'm sure you supervise in some of them as well.
Yes, I've seen quite a number of teams, and Jane, you're right. Those small initiatives are important. I think that the big research dollars are usually coming from established industries, from large enterprises, as you said, and those small grassroots ideas that you're discussing, as Chandra mentioned, are often the ones that are brought forward by the students under their own initiative. And you see them in senior design projects with the undergraduates. And so those are very important and very interesting. And a lot of the more innovative ideas often come from those grassroots projects as well. So
I think the challenge is, Jane, we've done a few pilots, a few models, the students have done a few pilots, a few models. It's how they scale it up to make impact in the community. I think that's where it all lies now, to take their ideas out onto a bigger scale at the community level.
Yeah, very good. So thank you, Jane. I've got your sound turned off. I'm sorry, but I'm just going to wrap things up for this evening, and I'll stop the recording in a moment. But again, I would like to thank Professor Madramootoo for taking the time to talk to us this evening. It's very appreciated. You can see by the number of people that have stayed right till the bitter end how interested we all are in your topic. And thank you to all of the audience for joining us. And again, I invite you to come back in 2 weeks, same time, same place for our next lecture. And I wish you a good evening.